Well, hello everybody, and welcome to day 2 of Ellipses. We have one objective for today, and that is to write the equation of the ellipse in standard form. So before we do that, let's review our two standard forms for the ellipse. We have a horizontal ellipse, and that standard form is x minus h quantity squared divided by a squared, plus y minus k quantity squared divided by b squared equal to 1. And we also have a vertical ellipse, and that standard form is x minus h quantity squared divided by b squared plus y minus k quantity squared divided by a squared, all equal to 1. So we're going to be choosing one of these two standard forms for each of our problems today. So let's figure out what we actually need to be able to plug into these standard forms. Obviously, we're going to need the center, since that is the values h and k. We can plug those into our parentheses. The other things we will need the value of a, so we can square it, and we'll need the value of b, so we can square it. So that's really it. We need hk, our center. We need the value of a, which can come from a couple different places, and the value of b. That's all that we'll need to do today. Let's look at our first example. Okay, so we are to write the equation of the ellipse that has one focus at 0, 2, and its vertices at 0, -3 and 0, +3. So I've got a little graph patch here because I think that visually this helps me. So I'm going to go ahead and plot these points. I know that my vertices are at 0, 3 and 0, -3. So 0, 3 is up here. I'm going to label that with the V for vertex, and 0, -3 is down here. I'm going to label that with the vertex. I instantly understand that I'm talking about a vertical ellipse. Let's go ahead and put the focus in. The focus is at 0, 2, so that's going to be right here, and I'm going to label that with an F. Again, this is enough for me to know that we are talking about a vertical ellipse, and therefore our standard form is going to be x minus h quantity squared over b squared plus y minus k quantity squared over a squared, all equal to 1. I know that the a squared is always our larger denominator, and this time the larger denominator needs to be with the y term since we are stretched in the y direction. Okay, if I have my two vertices, then I know that the center is going to be exactly halfway between those two vertices. So I know that my center is going to be right here. That happens to be my origin, so I know that my center is 0, 0. So that simplifies my standard form a little bit. I know that it's now simply x squared over something plus y squared over something equals to 1, because h and 0 are now, or excuse me, h and k are now zeros. So I don't need to put those into the standard form. Okay, now we need to figure out the value of a, and we need to figure out the value of b. Well, the value of a is not that difficult because once we have the center, we know that the value of a is the distance from the center to either one of the vertices. So this is my value of a, and in this case that's simply 1, 2, 3 units. So I know that a is 3. If a is 3, then that of course implies that a squared is 9, and I can put that into my standard form. A squared is going to turn into 9. Now I need to find b. b is the distance from the center to the covertices. Unfortunately, I have no way of knowing where the covertices are right now. But I do have the value of c. I do have this focus, and since that is exactly 2 units, I'll go ahead and put C right here. This is exactly 2 units from the center. I know that C is 2. And if I remember the relationship that C is the square root of a squared minus b squared, and I have the value of a and the value of c, I could plug those numbers into this relationship and go and solve for b. So let's do that. I know that c is 2, so this is going to be 2 is equal to, I know that a squared is 9, so this is 9, and then minus b squared. So this is a simple equation to go and solve for b. I do need to get to it, which means I need to get rid of this square root first. So I'm going to square both sides. Square that. Squaring a 2, of course, gives me a 4. Squaring a square root basically undoes that operation, and the radicand pops down. Now I need to solve for this b squared. Perhaps I actually add b squared to this side, and maybe at the same time subtract 4. So that's gone. I've got b squared is equal to 9 minus 4, which is 5. I could actually go and find b, but actually I don't need the value of b. I'm not graphing my thing. All I need is the value of b squared, because that's going to go right into our formula, and that's going to be a 5. We have our standard form for this ellipse. Let's practice this again with another problem. So here's our next problem. It says to write the equation of the ellipse with the center at 2, -3, one focus at 3, -3, and one vertex at 5, -3. Okay, let's go ahead and plot these things. Let's plot the center at 2, -3. That's 2, -3 is right here. It's real important, in my opinion, to label our points with little letters so we know which point is what. Okay, so we've labeled the center. Let's label one of the focal points 3, -3. So that's over here at 3, -3, and I'll label that with an F. Okay, and one of our vertices is at 5, -3. 1, 2, 3, 4, 5. -3 is one of our vertices. Okay, so given these 3 points, I now know that my ellipse is moving in a horizontal direction. So I know that this is a horizontal ellipse. That's the big clue that I see first. This is horizontal. Since it's horizontal, I know my standard form is going to be x minus h quantity squared over a squared plus y minus k quantity squared over b squared, all equal to 1. Okay, great. Now I do know my center already. My center gives me my h and it gives me my k, so I can go ahead and do the tops. Right now it's x minus 2 quantity squared over something plus y plus 3 quantity squared over something, all equal to 1. I just need to know what a squared is and what b squared is. Okay, well, given my distances in my picture that I've drawn here, it's pretty easy to go and find a. I do not know what b is yet, and it's pretty easy to go and find c. Sorry. Let's go ahead and figure out what a is. A is the distance from the center to either one of the vertices, and I have one out here, and it looks like, well, a is going to be 3 again. B is, oh, I don't know what B is. B is the distance to a covertex, and I don't have the covertices right now, but I do know what C is. C is the distance from the center to one of the focal points, which is right here, and that's just 1. So I know that A is 3, and I know that C is 1. Again, instantly I know that a squared, of course, is 9, so I can put that into my standard form. I know that the bigger number is going to be with the x. That's what makes my graph stretch in the x direction, so that's why 9 is going to go here. So I know that b squared is going to be something smaller than 9, but I'm not going to guess. I'm going to use my relationship with c being equal to the square root of a squared minus b squared. Very similar to our previous problem. C is the value of 1, so there it is. A squared, we already said, was 9. B squared, of course, is b squared until we know what it is. So let's go ahead and square. I need to get into the b squared, which is underneath the square root. So I'm going to square both sides. 1 squared becomes 1. The square root and the square cancel out, leaving 9 minus b squared. I can go ahead and add b squared to this side. I got b squared plus 1 is equal to 9. Then I can subtract the 1, and I got b squared equals 8. Now again, I can continue on and figure out what b is, and that might be helpful if I'm going to graph the covertices, but since that's not required here, I'm finished once I know what b squared is. And I can plug that right into my formula, and there's my 8. Here is my standard form for this ellipse. And let's move on to our third problem. Okay, so here is our final example for today, and I hope that this is working because my video capture window just went away. I'm hoping that this works. Okay, let's go ahead and read this. It says, there is a hall that has been designed to be a whispering chamber. The hall is 50 feet wide, and the elliptical ceiling begins 6 feet above the floor and extends 20 feet high at its center. Where are the foci located in this hall? I talked about the application of one application of ellipsoids, three-dimensional elliptical figures, was the whispering chamber or whispering gallery. There's actually a famous whispering gallery that is at the U.S. Capitol, and one of the interesting properties of an ellipse, if I draw the top half of an ellipse, let's say right here, and connect that. We've got the center, of course. We've got two focal points. You know, one of them's somewhere over here, and one of them is somewhere over here. What's interesting is that if you're standing on one of the focal points or near one of the focal points, and you're just talking, even if you're just whispering, if you're just talking just a little bit, the sound waves will bounce off the elliptical ceiling and go right through the other focal point. No matter where you're standing, no matter where you're pointing your voice at, they will all go through the other focal point. It's kind of a neat property of the ellipse, and I've got a video to show you. I just happened to go onto YouTube to find this. This is about a minute long, actually about 50 seconds long, and this is a tour that's happening in the US Capitol in the Whispering Gallery. So I'm going to maximize this so you can see, and we'll press play.
But we've noticed something about the area. I'm going to go to the other side of the room and you can join me in a few moments. But for now, I invite you to come in close and just lay your headphones around your neck. Please step up close.
So these students are standing on one of the focal points, and she's about to walk to the other focal point.
This room is often called the Whispering Chamber. If you can hear my voice on the other side of the room, please raise your hand. Thank you. Now you can join me on this side to put your headphones back on.
So that's a pretty cool example of an application of the whispering chamber of an ellipse. Okay, so let's actually solve this particular problem. We actually have no numbers in terms of a location where this ellipse is on our graph paper. So I still have my graph paper, and remember, we can put our center wherever we want. Ideally, our center could be at 0, 0, and in fact, that's actually what I'm going to do. Now, I only have a certain number of tick marks, and obviously I have to count out 50 units. So perhaps I actually change my, my scales. Perhaps on the x-axis I count by 5s. Perhaps on the y-axis, to keep it square, I also count by 5. Okay, so each tick mark is now representing 5 units. If this is the center, I do recall something in our problem. Yep, it says that the chamber extends 20 feet high at its center. So if this is the center, then 20 feet high would be up 5, 10, 15, 20. Okay, that would actually be a co-vertex because I know that we're talking 50 feet in this lateral direction. So 50 feet wide is the entire chamber. So since I'm in the center, I have to go 25 feet on each side. So 5, 10, 15, 20, 25, and 5, 10, 15, 20, 25. So this is representing the roof, or the ceiling, I should say, of my whispering chamber. Not necessarily the one, of course, in the US Capitol. This is another one that has been constructed. Now, also, one last little thing. This ceiling does not begin from the floor, of course. It begins 6 feet above the floor. Okay, so we're actually talking about, you know, there's vertical walls that are about 6 feet before this ceiling actually happens. So 6 feet would be about right here. So this is the floor. of our whispering chamber, and then our elliptical ceiling starts about 6 feet above the floor. But I put the 0, 0, or my origin is still going to be my center because I think that that's going to make a lot more sense. Okay, so we have to figure out where the foci are. That's what I'm looking for. And the focal points are C units away. So we really need to know what the value of C is. I know that the relationship between C, A, and B is that C is equal to the square root of A squared minus B squared. So if I knew what A and B were, then I would be able to find C pretty easily. Well, I'm pretty sure we can find A and B pretty easily. A is the distance from the center to one of the vertices, and it looks like that's 1, 2, 3, 4, 5 tick marks. But remember, each tick mark is representing 5 units, so that's actually 25 feet. That's what A is. And B is the distance from the center to one of the co-vertices. So if this is one of the vertices, this must be one of the co-vertices, and that's 1, 2, 3, 4 tick marks, which would represent 20 feet. So I know the values of A and B, so C should not be that difficult to go and find. A squared, 25 squared is 625. B squared is 400. So C is the square root of, if I subtract 625 minus 400, I get, hey, look at that, a nice perfect square. So it looks like C is going to be 15 feet. So since C is 15 feet, I know that my two focal points are 5, 10, 15 feet and 5, 10, 15 feet away from my center. I'm actually going to draw nice little stick figures here to represent people that may be standing at each focal point trying to talk to each other. Okay, so word problems end in words, and I do not see any words yet. So I have to answer in words. The foci are located 15 feet away from the center, and I might say horizontally, and don't forget 6 feet above the floor. That's where our foci in this whispering chamber are going to be located, 15 feet away from the center and 6 feet above the floor. So pretty cool application for ellipses. Thanks for watching that one. I'd like to end this lesson with 3 try problems. If you could please pause this tutorial at this point and try your hand at each of these 3 try problems. Take some time and then come and restart the video to see that you've gotten your correct answers. Please pause now. Okay, thanks for trying these, and here are the correct standard forms for these 3 problems. Notice that the first 2 are horizontal ellipses. I know this because a squared was the bigger number, and that's underneath the x in each one of these. We used major axis in these second 2 examples or tries. The major axis, remember, is the longer axis, and it's exactly 2 times the value of A. So since the major axis is 6, I know that A is half of that, and since the major axis here is 8, I know that A is half of that. Notice that in try 3, though, that we're talking about a vertical ellipse if you graphed the pieces. Thanks for watching this tutorial. I'll see you in class and we will practice more of that. Bye-bye, everybody.